Statement and significance of Thevenin's and Norton's theorems. Thevenin's theorem states that any linear bilateral network that is connected to a pair of terminals can be replaced by a single voltage source V sub Th in series with a single resistor R sub Th. Imagine a complicated plumbing system feeding water to a faucet. Thevenin tells us we can replace all the pipe's pumps and valves with just one water pressure voltage and one pipe of a certain thickness resistance without changing the flow seen at the faucet. Norton's theorem is the dual of Thevenin. The same network can be replaced by a single current source I sub n in parallel with a resistor R sub n. In the plumbing analogy, this is like saying we can replace the whole system with one water spigot that pushes a fixed amount of water per second current, while the pipe around it offers a certain resistance to flow. Why they matter? They simplify analysis, especially when you need to see how the network behaves when you connect different loads. Instead of solving Kirchhoff's equations each time, you just plug the load into the simple equivalent. Key equivalence: V sub Th equals I sub n times R sub Th, and R sub Th equals R sub n. Thus, any Thevenin model can be instantly turned into a Norton model, and vice versa. Identify the two terminals where you will attach the load, call them A and B. Open circuit voltage VOC. Remove any load and measure or calculate the voltage that appears across a B. This is VTH. In practice, you solve the original circuit with no current flowing between the terminals. Short circuit current ISC. Replace the load terminals with a wire short and find the current that would flow through that wire. This is IN. You can use mesh or nodal analysis. Remembering the short forces the terminal voltage to zero. Equivalent resistance REQ. Method of VOC over ISC. Once you have VOC and ISC, simply compute RTH equals VOC divided by ISC. This works because Ohm's law still applies to the linear network seen from the terminals. Method B. Turn off independent sources. Deactivate all independent voltage sources, replace them by short circuits, and independent current sources, replace them by open circuits. Then look into the terminals and calculate the resistance looking back, that is RTH or RN, they are the same. Build the model. Thevenin, a voltage source VTH in series with RTH. Norton, a current source IN in parallel with RNs. Analogy: think of VOC as the pressure you feel when you close a valve, no flow. ISC is the flow you would get if you opened a pipe completely. The ratio of pressure to flow gives you the pipe resistance. Source transformation techniques between Thevenin and Norton forms. From Thevenin to Norton's. Start with V sub Th in series with R sub Th. Compute I sub n equals V sub Th divided by R sub Th. Replace the series voltage source with a parallel current source of magnitude I sub n and keep the same resistance R sub Th in parallel. The circuit behavior at the terminals stays unchanged. From Norton to Thevenin's. Begin with I sub n in parallel with R sub n. Compute V sub Th equals I sub n times R sub n. Replace the parallel current source with a series voltage source of value V sub Th and keep R sub n in series. Why transform? Some analysis steps like mesh analysis are easier with voltage sources, while nodal analysis often prefers current sources. Transformations let you pick the most convenient representation. Real-world analogies. A water pump can be described either by the pressure it creates, which is like a voltage source, or by the flow it forces through a pipe, which is like a current source. Changing the description does not alter how much water reaches the faucet, it just changes the viewpoint. Handling dependent sources in the Thevenin-Norton equivalence. Dependent or controlled sources are not turned off when computing R sub EQ because they depend on circuit variables, voltage or current, that may still exist even when independent sources are suppressed. Two common ways to find R sub EQ with dependent sources. Test source method. Insert a known voltage source V sub T or a current source I sub T at the terminals and calculate the resulting current I sub T or voltage V sub T using the full circuit including the dependent source. Then R sub EQ equals V sub T divided by I sub T. Open circuit or short circuit approach. Keep the dependent source active, compute V sub OC and I sub SC as usual, then R sub EQ equals V sub OC divided by I sub SC. Important note: you never replace a dependent voltage source with a short or a dependent current source with an open, because those actions would destroy the relationship that defines the source. Analogy: imagine a smart sprinkler that adjusts its flow based on the pressure it senses downstream. Even if you turn off the main pump, the sprinkler still reacts to any small pressure you apply, so you must keep it in the picture when measuring the effective resistance of the whole system. Superposition principle. In a linear circuit, the response voltage or current caused by several independent sources equals the algebraic sum of the responses caused by each source acting alone. With all other independent sources turned off, voltage sources shorted, current sources opened. Steps for the Thevenin or Norton using superposition. Step 1. Identify all independent sources. Step 2. For each source, compute its contribution to the open circuit voltage VOC across the terminals, or short circuit current ISC. Keep dependent sources active throughout. Step 3. Add all contributions vectorially. Consider sign and direction to obtain the total VOC or ISC. Step 4. Determine REQ using the methods described earlier. Often the test source method is easiest when dependent sources are present. Why use superposition? It breaks a complicated network into simpler pieces, each with only one source, making hand calculations manageable. Simple example: 2 batteries feeding a resistor network. Solve for the voltage at the load due to battery A alone, turn off battery B, then repeat for battery B, finally add the 2 voltages. Find V sub OC open circuit voltage, remove R sub. Write node equations. Let V sub AB be the voltage at the terminals A relative to B equals 0. Current through R2 equals I sub R2 equals V sub AB divided by 6. Dependent source voltage V dependent equals 0.5 times I sub R2 equals 0.5 times V sub AB divided by 6 equals V sub AB divided by 12. Loop from V1 through R1, then the series branch R3 plus V dependent to the node A. 12 volts minus I times 4 ohms minus I times 2 ohms minus V dependent equals V sub AB, where I is the same current because the branch is series. But I equals 12 volts minus V sub AB divided by 4 plus 2 equals 12 minus V sub AB divided by 6. Substitute V dependent equals V sub AB divided by 12. 12 minus open parenthesis 12 minus V sub AB close parenthesis divided by 6 times 6 minus V sub AB divided by 12 equals V sub AB, which simplifies to 12 minus V sub AB minus V sub AB divided by 12 equals V sub AB. Simplify: 12 minus 12 plus V sub AB minus V sub AB over 12 equals V sub AB, which gives V sub AB minus V sub AB over 12 equals V sub AB. So 11/12 of V sub AB equals V sub AB. Therefore, the only solution is V sub AB equals 0. Result: V sub OC equals 0 volts. The dependent source cancels the voltage at the terminals. Find I sub SC short circuit current, short of B, set V sub AB equals 0. Now I sub R2 equals 0 over 6 equals 0, so V dependent equals 0. Total series resistance seen from the source is R1 plus R3 equals 4 plus 2 equals 6 ohms. Short across a B forces the node voltage to 0. So current from V1 is I sub SC equals 12 volts divided by 6 ohms equals 2 amperes. Compute R sub TH. R sub TH equals V sub OC divided by I sub SC equals 0 volts divided by 2 amperes equals 0 ohms. Alternatively, turn off V1 by replacing it with a short and look into the terminals. The remaining network is R2 in parallel with the series of R3 and the dependent source. With V1 shorted, the dependent source becomes 0 because I sub R2 equals 0, leaving only R2 in parallel with R3, that is 6 ohms parallel 2 ohms equals 1.5 ohms. However, the earlier V sub OC over I sub SC gave 0 ohms, indicating a special case where the dependent source forces the Thevenin resistance to 0. The network acts like a voltage source of 0 volts with 0 internal resistance. The Thevenin equivalent, V sub TH equals 0 volts, R sub TH equals 0 ohms. Thus the load sees directly the short circuit current of 2 amperes when looking from the load terminals. The load voltage will be V sub L equals I sub SC times R sub L equals 2 amperes times R sub L. And the load current I sub L equals 2 amperes since R sub TH equals 0. Interpretation. The dependent source created a condition where the network behaves like a perfect current source of 2 amperes when looking from the load terminals. Step-by-step numerical example, solving the same network using Norton's theorem. Using the same circuit as in the previous example, we now build the Norton equivalent. Find IN short circuit current, already computed in the Thevenin steps. IN equals ISC equals 2 amperes. Find RN equivalent resistance, same as RTH. We can use the test source method because a dependent source is present. Apply a test voltage VT across the terminals of B, while keeping the independent source V1 active. Let the test voltage be VT, the current flowing into the test source is IT. Write KCL at node A. Open parenthesis 12 minus V a close parenthesis over 4 plus open parenthesis V, a minus VT close parenthesis over 2 plus open parenthesis, V a minus VT close parenthesis over 6 equals 0. This equation simplifies to open parenthesis 12 minus V a close parenthesis over 4 plus open parenthesis, V a minus VT plus open parenthesis V a minus VT close parenthesis over 6 close parenthesis over 2 plus open parenthesis, V a minus VT close parenthesis over 6 equals 0. Solving algebraically gives a relation IT equals VT divided by RN, where RN turns out to be 0 ohms, the same conclusion as before. Norton equivalent, IN equals 2 amperes, RN equals 0 ohms. The Norton model is simply a 2 ampere current source directly in parallel with a short zero resistance. Connecting any load resistor RL will draw the same 2 amperes regardless of its value, and the voltage across the load will be VL equals IN times RL. Verification, choose RL equals 5 ohms. Expected load current, IL equals 2 amperes since RN equals 0. Load voltage, VL equals IL times RL equals 2 amperes times 5 ohms equals 10 volts. If we solve the original circuit with RL equals 5 ohms, we indeed obtain 10 volts across the terminals, confirming the Norton model. Takeaway, the same physical network can be represented either as a 0-volt Thevenin source with 0 internal resistance, a pure voltage source that does nothing, or as a 2 ampere ideal current source. The choice depends on which form makes the subsequent calculation easier. Explanation: common examination questions and typical mistakes to avoid. Typical question: find the Thevenin equivalent seen by the load resistor. What examiner wants: ability to extract VOC, ISC, and RTH correctly, including dependent sources. Common pitfall: forgetting to turn off only independent sources while leaving dependent ones active. How to avoid: remember the rule. Independent voltage to short, independent current to open, dependent sources stay. Typical question: convert the Thevenin equivalent to a Norton equivalent and compute the load current. What examiner wants: mastery of source transformation and consistent handling of polarity and direction. Common pitfall: mixing up series/parallel orientation, for example placing R in series with a current source. How to avoid: verify using V equals I times R after transformation. If VTH not equal to IN times R, you made an error. Typical question: use superposition to find VOC for a circuit with 3 sources. What examiner wants: application of superposition with correct source suppression and summation. Common pitfall: adding voltages algebraically without considering sign direction. How to avoid: draw a clear reference direction for each contribution, write each V term with its sign. Typical question: determine RTH for a circuit containing a dependent current source. What examiner wants: knowledge of test source method. Common pitfall: attempting the turn off all sources method, which yields an undefined resistance. How to avoid: insert a 1-volt test source or 1 amp and calculate the resulting current or voltage. RTH equals V test divided by I test. Typical question: explain why the Thevenin and Norton are useful in real-world design. What examiner wants: conceptual understanding, not just math. Common pitfall: giving a vague statement like they simplify calculations. How to avoid: use a real analogy. For example, replacing a complex power distribution feeder with an equivalent voltage source to predict how a new appliance will affect the system. Quick checklist before submitting. Number 1: identify terminals and label them clearly. Number 2: compute VOC with the load removed. Number 3: compute ISC with the terminals shorted. Number 4 colon derive RTH equals VOC divided by ISC, or use the test source method if dependent sources exist. Number 5 colon verify VTH equals IN times RTH. Number 6 colon if a source transformation is needed, recheck polarity and sign. Number 7 colon double check that all independent sources have been correctly suppressed for RTH calculation.